Okay, so that's it. Solid conductors, the current is carried by negatively charged electron. Electrolytic solution, the current is carried by the positive and negatively charged ions. When no field is applied, so remember, no electric field is applied, the electrons are in random motion, and the average velocity of charges is 0. It becomes 0. Okay, so therefore there will be no net current. So that is the reason. 3 stages are there. One is in solid conductors. It is moving, negatively charged electrons are moving, so current happens. Electrolytic solution, it is carried by the ions. And if there is no electric field, it will be in random motion. The average velocity reduces to 0. So that's then drift velocity. It's another important term we have to remember. It is the average velocity with which electrons in a conductor move opposite to the direction of electric field. Average velocity with which electrons in a conductor move opposite to the direction of electric field. Then when it is in an electric field, when the electrons are in an electric field, it will experience a force in the direction opposite to the applied electric field. The reason is that F, we know F equals Q into E. The value of Q is minus E. So the force will be minus Q into E. So it is experiencing a force opposite to the direction of electric field. So electrons are moving opposite to the, see, electric field is in this direction. Electrons are moving opposite to the direction of electric field in a conductor. So if we can consider a conductor of length L, area of cross section capital A, across which an electric field E is present due to potential difference V, then the force acting on an electron will be, as explained here, it is minus EE. So Q is equal to minus E. So that will be minus E times capital E. So acceleration produced in the free electron due to the electric field, how much it will be? Acceleration, it will, so we can write any force which is equal to mass into acceleration. So acceleration is equal to force by mass. So force is minus E divided by mass, it is minus EE divided by, yeah, minus E capital E divided by, yeah. So here the E is charge of electron and capital E is the electric field. That all you know. Okay, now the next one. So the drift velocity, the velocity with which electrons are being drifted through that, this one is called drift velocity. So during the movement of the electrons will undergo continuous collisions. See, continuous collisions. When it is moving from one point to another point, it will undergo continuous collisions. So the velocity of electrons remains only for a short interval of time between two successive collisions. So if it is undergoing continuous collisions, the time interval between two successive collisions we have to consider. Okay, the average time interval between two successive collisions of free electrons is called relaxation time. tau. The average time interval between two successive collisions. It is called relaxation time tau. Now, therefore, the drift velocity of electrons can be calculated. It is a method to calculate the drift velocity. We are using the equation of motion for that. The equation of motion is u, that v, final velocity, equals u plus a multiplied by t. This is final velocity, this is initial velocity, acceleration, and the time taken. So here in the case of this particular example, u, the initial velocity, is 0, and v is the drift velocity we are considering, and a, of course, a is equal to E capital E divided by m. So let us see. So this is the equation we are using. V equals u plus at, and the drift velocity u is 0 here, and a is this one. A is E by m into multiplied by tau. So this comes to be drift velocity equals small e, that is the charge of electron, capital E, that is the electric field, by mass multiplied by relaxation time. Okay, is it all right? See, the drift velocity, we got it as E by mass multiplied by tau. So this is a conductor, and this much is the area of the conductor, area of the conductor, and this is the length of the conductor, length of the conductor. Small conductor we are taking, and let's see, the electric field is towards right. Remember, electric field is towards right, and an electron is moving here towards left. Okay, electron will move opposite to the direction of electric field. We explained it already. Now we take a small section. So we know that velocity equals delta x divided by delta t. So delta x will be equal to Vd multiplied by delta t. So that we have small distance we are considering. Small distance we are considering. That small distance is Vd multiplied by delta t. Then, if n is the number density of free electrons, n is the number density of free electrons. Then we can say that if we take a small interval of time delta t, we can have the number of electrons crossing an area of cross section in this time. Number of electrons crossing an area of cross section in this time is n is the number density multiplied by a into Vd into delta t. This Vd into delta t is delta x. Okay, so a is the area. So number density multiplied by area multiplied by that length. So it gives the total number of electrons crossing an area of cross section in a particular time interval. So that will be equal to q. So this is the number, and now the charge of this much number of electrons. This is the total number, and the charge of this much number of electrons, it will be equal to this number multiplied by charge of each electron. So that will be Na Vd delta t multiplied by charge of an electron is E. So this is the total charge of this much electrons. Then electric current will be equal to we know that it is the charge upon time. Electric current is charge upon time. So this is the total charge. Now we have to divide it with the time. We get total charge Na Vd delta T into E divided by delta T. So we get an equation for the current. Current I equals N number density, A area, Vd drift velocity, and E the charge of an electron. So this is an equation for current in terms of drift velocity. Equation for current in terms of drift velocity. JNV Belgavi is saying that the lower part of the board is not visible. Okay, let me check it. It is visible, no? Visible. Yeah, it's visible. No issue. Okay. Is it correct? Is it clear? Now let's move on to next one. So we have developed an equation I equals Na Vd multiplied by E, and we have the equation for drift velocity. It is Ee upon m multiplied by tau. Tau is a relaxation time, and we know the electric field. Electric field is potential difference upon unit time. So there we can write the equation for I as substituting the value of Vd. Vd is to be substituted. Then we can write I as Na. Instead of Vd, we will write E capital E upon m multiplied by tau, and one more E is there. So we get a relation like this. I capital I equals Na E square capital E upon m multiplied by tau, the relaxation time. So when we adjust all these things, we get a value like this. This electric field, see, electric field can be written as V upon L. V is the potential difference upon length. So when we substitute that value, we get Na small e charge of electron, then potential upon m mass as well as length upon multiplied by T. Then from this equation, we get V equals ml capital I upon Na small e multiplied by relaxation time tau. Now we know that V equals R into I from Ohm's law equation. V proportional to I from Ohm's law equation. Then we can write R equals, see, in this equation, when we compare these two equations, this can be taken as ml by Na E multiplied by T. So that can be taken as R. These two are similar. This one, these two are similar. And now coming to this equation, we have rearranged this and removing L and A. These are variables. L and A are variables. Then we can attach m N E square tau. When we take it as a constant, we get a new constant called resistivity. Resistivity rho into L by A. Rho multiplied by length divided by A. Is it okay? Rho is the resistivity of the material. Now the Ohm's law. Of course, we studied Ohm's law in class 10. basic facts we have studied. Still, we want to move on to the applications of Ohm's law. There is a resistor. The basic things required in Ohm's law is resistor, voltmeter, ammeter, and supply. Resistor, voltmeter, ammeter, and supply. Okay, so electric current I flowing through a conductor is directly proportional to the potential difference V across the two ends of the conductor. Okay, the physical conditions like temperature, entropy, all other parameters should remain as a constant. So that is the basic definition of Ohm's law. So this is the result. I is a result and V is the cause. Okay, that's so we write it as I proportional to V, and we can also write V proportional to I then V can be taken equal to a constant R multiplied by I. Then the constant of proportionality R is called the resistance of the conductor. Constant of proportionality R is called the resistance of the conductor, and the SI unit of resistance is ohm, OHM. The symbol OHM, ohm. So this is the graph of Ohm's law. See here, different V and I. It is varying linearly with the V. I is varying linearly with the V. And we can take a slope of this one, delta Y divided by delta X. Okay, so this one is delta V, and this is delta I. We can take slopes like that. And delta V by delta I is called the resistance. Then 1 ohm is the resistance of a conductor which develops a potential difference of 1 volt. So R, we know R is equal to V by I, that is 1 volt upon 1 ampere, that is equal to 1 ohm. Okay, so 1 ohm is the resistance of a conductor which develops a potential difference of 1 volt when a current of 1 ampere passing through it. Now, the resistance of a conductor depends on certain parameters. What are the parameters on which the resistance of a conductor depends? So that is, first one is length of a conductor. That means if a conductor is having this much length and this much length, this is L2 and this is L1. So this will have more resistance, R2, R1. So R2 will be greater than R1. So length increases, resistance also increases. Next case is, so that is why R is proportional to L. R is proportional to L. Next one is area of cross section of a conductor. It is inversely proportional to area of cross section. See here, R is inversely proportional to area of cross section. That means you have a small wire and a bigger one. So here the area of cross section is A1. Here the area of cross section is A2. And we know that A2 is greater than A1. Since R is inversely proportional to A, which one of these two will have a lesser resistance? Which one of these two will have a lesser resistance? Of course, this one will have a lesser resistance. So this R2 will be lesser than R1. So area of cross section, radius is inversely proportional to resistance. As the radius increases, resistance decreases. Radius increases, resistance decreases. Now the third one is temperature of the conductor. At a constant temperature, yeah, this is the same thing as that of this one. Okay. So it depends on 3 parameters. One is length of conductor. Second one is area of cross section of conductor. Third one is temperature of the conductor. As the temperature goes up, resistance also increases. So we can combine these 2 things and we can write R is proportional to L. R is proportional to 1 by A. We can combine these 2 things and we can write R proportional to L by A, and we can write R is equal to rho into L by A. Rho. Rho is the resistivity. So remember, R is directly proportional to length, inversely proportional to area of cross section, directly proportional to temperature, and R equals rho resistivity multiplied by length upon area. I think it is clear. Now let's move on to the next one. Rho is called the resistivity for the specific resistance. See the unit of resistivity. Unit of resistivity. So resistivity can be written as Ra by L. So it is ohm meter. Unit of resistivity is ohm meter. Now the comparison between resistance and resistivity. First one is resistance. It is a property of a substance. By virtue of it, it opposes the flow of current. Okay, so resistance is a property of a material to oppose the flow of current. Its unit is ohm, and there are certain factors which affect the resistance of a conductor. Okay, so resistance property, unit is ohm. There are certain factors which affect the resistance of a conductor. And now coming to resistivity, it is the property of the material. Here it is the substance. Here it is the material. The difference is that we can have different kinds of resistors by using the same material. Okay, by using copper, we can construct different types of resistances of different values. Whereas in the case of resistivity, for all those resistances we made from copper will have the same resistivity. Okay, so resistivity is a constant for a material, whereas resistance is depending upon the type of resistors. Okay, so it is defined as resistance of a conductor of unit length and unit area of cross section. Okay, it's the resistance of a conductor of unit length and unit area of cross section. Its unit is ohm meter, where the unit is ohm. Factors affecting resistivity are temperature, number density, type of conductor. Three things: temperature, number of electrons per unit volume, number density, then the type of conductor. So these are the parameters on which resistivity of a material depend. Now the current density. Current per unit area. Current per unit area is called current density, I upon A, current per unit area. SI unit is, current is ampere and area is meter square, so it is ampere per meter square. Okay, so current density is denoted by the letter J. Okay, as per Ohm's law, V can be taken as I multiplied by R. Then instead of R, we can write rho multiplied by L upon A. Then I upon A is called current density J. Then we can rewrite the equation as V equals rho, that is the resistivity, multiplied by I multiplied by J. Then if we introduce the E, the uniform electric field of the conductor of length L, then that equation changes to V equals E multiplied by L. Then instead of V, we are substituting this equation. This comes here, J rho L. That L and L gets cancelled. This L gets cancelled. So we write E equals J rho. Okay, so electric field is a vector. So vector E equals J rho. Rho is a scalar quantity. So obviously J will be a vector. Okay, so J equals E upon rho, that is 1 by rho. It is called conductivity sigma. 1 by rho is called conductivity sigma. The SI unit of conductivity is, see, in the case of resistivity, the unit we have taken as ohm meter. So in the case of conductivity, the unit is, it comes in the opposite way. That last letter is M. So here the first letter is M, middle letter is H, middle letter is H, first letter is O, last letter is O. And here it is meter, so it will be meter inverse. So these are the units of resistivity and conductivity. This is ohm meter, that comes in the reverse way, MHO, M raised to minus 1. There is another unit for conductivity also, that is Siemens per meter. Okay, we'll move on. Now next is the mobility. See, the conductivity of a conductor, what is the reason for the conductivity of a conductor? It is because of the mobile charge carriers. The charges are moving in a conductor, so it is because of that only we get conductivity. And the mobility is defined, mobility of these charge carriers, it is defined as the magnitude of drift velocity per unit electric field. Drift velocity per unit electric field is called mobility. Drift velocity per unit electric field. See, drift velocity upon electric field, it is called drift mobility. Then Vd can be substituted with Vd okay, so this can be substituted here, and the unit of mobility is meter square per volt second. V is volt and S is the second. Okay, so in this you substitute the value of Vd and you will get the value of drift mobility. Now the limitations of Ohm's law, just go we will go in brief. But in some materials and devices, it does not hold true. In some materials like semiconductors, such kind of materials, Ohm's law will not hold true. There are two basic categories of circuit elements. One is ohmic and second one is non-ohmic circuits. So ohmic circuit means the circuits which obey Ohm's law, and non-ohmic circuit means the circuit which does not obey Ohm's law. Okay, so these are the two types of circuits. See, this is the particular graphical representation of Ohm's law. In the x-axis, current is taken and y-axis, voltage is taken. The blue line represents the real observations, and the dotted line represents the theoretical or the ideal representations. In the ideal case, it should be a straight line. It should be a straight line. And in the real situation, it will be a straight line under normal voltage and current. And if the current increases to a greater value, it deviates from its ideal behavior. So that is one of the limitations of Ohm's law. At high temperatures and all, it does not obey the linear nature. And see here, in this case, this is a case of a semiconductor. Here it is not linear. After a particular voltage, it increases rapidly, and for the negative side, it is not linear. So this is another example of the limitations of Ohm's law. It is not valid in all circuit elements, and in all kind of applications and all these things. That is another limitation of Ohm's law. See this one. This is another example. This graph has two kinds of region. See, this is non-linear here. This is again non-linear here. Here, as the voltage increases, current increases. So we can have a positive value of resistance here. Here, when the voltage increases, see here, from this point to this point, when the voltage increases, current is decreasing. Voltage increases, current is decreasing. So when we take delta I here, we will get a minus value, negative value. So, okay, then delta I by delta V. If we take delta V by delta I, resistance equals delta V divided by delta I. It is equal to delta V. If we take, so delta V divided by the delta I means this one, this one. So this is the final point. If we take 2 minus 1, final point minus initial point, this will be a negative value. So we will get minus R. So this is a negative resistance region. So this is a positive resistance region. So it will have both the regions in the same plot, positive resistance region as well as negative resistance region in the same graph. So that is another limitation of Ohm's law. So remember limitations. 1, at high voltages and currents, it deviates from the actual behavior. It is showing different types of relationship for positive as well as negative voltages. For positive voltages, it is showing one kind of relation, and negative voltage, it is showing another kind of relation. So this is another limitation. And for the same plot, it is showing positive resistance region and negative resistance region. So this is another limitation of Ohm's law. 3 different types of limitations. Now the commercial resistors, how we make resistors. Okay, so commercial resistors are of 2 major types. One is a wire bound resistor. It is made by winding the wires of an alloy. Commonly used alloys are manganese and nichrome and constant. In manganese, nichrome and constant we use. And these resistances are in the range of a fraction of an ohm to a few hundred ohms. Okay. The second category is carbon resistors. They are made from carbon. They are compact, inexpensive, and small in size. Okay. Now, the comparison of EMF and potential difference. See the different statements. EMF is the maximum potential difference between 2 electrodes when no current is drawn from the cell. Maximum potential difference between 2 electrodes when no current is drawn from the cell. Open terminal potential difference, it is called EMF. Okay, whereas the potential difference is the difference of potentials between any 2 points in closed circuit when a current is flowing through the circuit. Then EMF is independent of the resistance of the circuit, independent of the resistance of the circuit. Now, the potential difference, it is proportional to the resistance between the given points. So we know that V equals I into R. So it is proportional to the resistance between the 2 points. Then the term EMF is used only for the source of EMF, for a cell, for different types of cells and all these things. Okay. Then the potential difference is measured between any 2 points of the circuit. Then the last one, it is commonly EMF is greater than the potential difference between any 2 points in a circuit. But in the case of potential difference can be greater only when the cell is recharged. Cell is given some charge from an external battery. Okay, so potential difference is greater only when the cell is being recharged. But EMF will always be greater than the potential difference. So this is a very important comparison. Commonly CBSE asks some, at least 1 or 2 mark questions from this area. You can note down these different points, EMF as well as potential difference. It will be worthy enough for the exams. Okay, now the color code of carbon resistors. Of course, this is not included in our syllabus. We are not expecting any questions also. It is for the basic awareness I am presenting, because if we know all these basic facts, then only we can propagate into new ideas with much speed. Okay, so there are three different lines. First one is a digit. This one is a digit line. Second one is again the digit line. Third one is a multiplier. This is the tolerance level. Okay, so different numbers are assigned to the different color. Black with a number of 0, brown 1, like that. White has got a number of 9. Then different tolerance level is also given. If it is golden line, we have a tolerance of 5%. And if it's a silver line, we have a tolerance of 10%. And if there is no line, there will be a tolerance of 20%, like that. So 3 lines will be there. So we can read the lines. The third line is a multiplier, and the multiplier value also given there. If it is a black, it has got a value of 1, and if it is brown, we have to multiply this reading of these two lines with 10. And if it is a red line, we have to multiply the value of these two lines with 100. So it is 10 square. So like that. Now, resistivity of a conductor, another important parameter. So resistivity, the range is 10 power minus 8 ohm meter to 10 power minus 6 ohm meter. Resistivity increases with the temperature. Remember, resistance as well as resistivity increases with temperature. Okay, so resistivity over a limited range of temperature is given by rho T. Rho at a particular temperature equals rho 0. It is 0 degree plus multiplied by 1 plus alpha T minus T0, where T minus T0 is the difference in temperature. Okay, rho T is the resistivity of that particular material at a given temperature. Rho 0 is the resistivity at temperature T0. And alpha is the temperature coefficient of resistance. So dear children, for the past 2-3 years, this equation becomes very popular because every time we expect a question from this area for the past 2-3 years. Okay, SI unit of alpha, the temperature coefficient of resistance, is Kelvin inverse. Okay, how the resistivity varies in the case of copper, you see, x-axis temperature is taken, in y-axis resistivity is taken, and it is giving an exponential increase. This graphs as it is, they will ask for the exam. Show the plot between resistivity and temperature of copper, like that they will ask, or variation of resistivity with temperature of copper, or any other thing they can ask. So this is a common tendency nowadays. Copper and nichrome are given. See, the case of copper, it is giving a curve, whereas in the case of nichrome, it is a line. So which is having more stability in the case of temperature. So this is giving a linear relation only, whereas this gives an exponential increase. Okay, so this is more preferable at high temperature applications, and this is more preferable for making resistors. These graphs as it is, they ask at the board exam. Now the semiconductors, resistivity is in between that of conductors and insulators. In the case of semiconductors, resistivity comes in between that of conductors as well as insulators. Okay, so resistivity decreases with increase in temperature. So this idea or this concept is being used in making all the semiconductor devices. In the case of semiconductors, resistivity decreases with increase in temperature. Remember, in the case of conductors, resistivity increases with increase in temperature, whereas in the case of semiconductors, resistivity decreases with increase in temperature. See this one, see the graph. Resistivity decreases with increase in temperature. This is temperature, and in the y-axis we have resistivity. It decreases with increase in temperature. Now, the variation of resistivity with temperature for different materials. I'm sure that one of this graph will appear in exam. Damn sure. Okay, see that 3 different materials are given: copper, nichrome, and a semiconductor. Okay, so copper, it gives an increase. It is a conductor. Copper is a conductor, so it increases, resistivity increases rapidly with temperature. Whereas nichrome is an alloy. In the case of an alloy, resistivity increases linearly with the temperature. And in the case of semiconductors, resistivity decreases with increase in temperature. Understand these graphs in a concrete manner, because these things will come in exam. Now, the combination of resistors, of course, this is not included for your class 12 syllabus. Still, we need to have a basic idea, because without this, we cannot proceed. So 3 resistors R1 and R2, R1, R2, R3 are connected combined in series. Then the effective resistance will be sum of the individual resistors. So if they are connected in series, the effective resistance will be the sum of the individual resistors. If 3 resistors are there, then R1 plus R2 plus R3. If 3 resistors of 2 ohms are connected, then 2 plus 2 plus 2, it will be 6, like that. And if they are connected in parallel, see, 3 resistors are connected in parallel. So the equation is like this: 1 by R parallel equals 1 by R1 plus 1 by R2 plus 1 by R3. But instead of looking at this one, 1 by R equals 1 by R1 plus 1 by R2 plus 1 by R3. Instead of this one, if 2 resistors are there, instead of this one, we can write R1, R2 by R1 plus R2. Okay, so better remember this equation. If 2 resistors are connected in parallel, then effective resistance will be equal to R1, R2 by R1 plus R2. Now let's try first one 2 ohm, second one 2 ohm. If it is connected in series, it will be 4 ohm. And if it is connected in parallel, if 2 ohm and 2 ohm are connected in parallel, then R parallel will be equal to R1, R2 by R1 plus R2, that is 2 into 2 by 4. So that will become 1 ohm. Okay. So if 2 resistors of equal values are connected in parallel, then their effective resistance reduces to half. And if they are connected in series, it becomes double. So that is a logic. So it becomes easy for you to calculate at the time of examination. Okay, now the electromotive force. There will be 2 electrodes for any cell, positive electrode as well as negative electrode. And this is the potential difference between the positive as well as negative electrodes of a cell when we do not take any current. That means when the cell is in an open circuit, okay, we are not taking any current. So that potential difference is called electromotive force. It is the potential difference between the positive and negative electrodes of a cell when no current is taken from the cell, no current is drawn from the cell. So we can simply call it as open terminal potential difference. That is called electromotive force. See this one. Okay. So terminal potential difference is V. The open terminal potential difference is E. Okay. When a current is flowing, or when a current is taken from the cell, then that is called potential difference. When no current is taken from the cell, that is called EMF E. See, this is E. No current is taken from the cell. Now we are closing the switch. Now this becomes V. Current is taken from the cell and it becomes V. Okay. Remember once again, this is E because no current, switch is open, no current is flowing or no current is taken from the cell. So it is open terminal potential difference, that is E, electromotive force. And when we take a current, when we close the switch, we generally take a current. Then the current flows through the circuit and that becomes V. So that is the difference between E and V. So open terminal potential difference is called electromotive force. That means when no current is taken from the cell, that is called electromotive force. Then internal resistance R. So that is another important parameter we have to remember, internal resistance. So it is the resistance offered by electrolyte of the cell when the current flows through it. Okay. So this is generally represented by small letter R. Normally we represent resistor by capital letter, but in the case of internal resistance, we represent it by small r. So it is the resistance offered by electrolytes of a cell, because the charges are flowing through the electrolyte and electrolyte offers certain resistance, that is called internal resistance. Okay, so this is another important parameter. This we can expect at the time of exam. Okay, the factors affecting internal resistance of a cell. What are the factors which affect the internal resistance of a cell? Then first one is larger the separation between the electrodes of a cell. Electrodes, larger separation is there. See, if this is the electrolyte and this is the electrodes, larger distance is there, larger separation is there, it is wide apart, the larger separation is there, then the internal resistance also will be larger. And greater the conductivity of electrolyte, this electrolyte is highly conducting, then obviously it will be lesser, internal resistance will be lesser. Then the internal resistance of a cell is inversely proportional to the common area of the electrodes in the dipping in the electrolyte. See, these electrodes are there now. This area which is dipping inside the electrolyte, the area of the electrode which is inside the electrolyte, it is depending upon that. Okay. Then the last point, internal resistance of a cell depends on the nature of the electrodes also, nature of the electrode. Okay, so these are the four factors which affect the internal resistance of a cell. Once again, the first one is separation between the electrodes, then conductivity of the electrolyte, common area of the electrodes inside the electrolyte. As the separation between the electrodes increases, internal resistance increases. As the conductivity of electrolyte increases, internal resistance decreases. Then it is inversely proportional to the common area of the electrodes dipping the electrolyte. So this you have to remember. There is a 90% chance for this at the board exam. Now, the relation between EMF and terminal potential. Remember, EMF is the open terminal potential, whereas potential difference is the product of voltage and current when current is taken. Sorry, potential difference is the product of current and resistance. So there must be a current in considering the potential difference. And EMF, no current is required. It is the open terminal potential difference. See, there is a cell of EMF E and there is internal resistance of small r. The voltage is V and EMF is E. Okay, and the current is flowing in the anti-clockwise direction. Now, which one is producing the potential difference here? The potential difference is produced by the current. So current is flowing through the internal resistance, it is flowing through the cell, it is flowing through the external resistance. So it produces a potential difference here as well as potential difference here, because we know V proportional to I and V equals I multiplied by R. So wherever there is a current, there will be a potential difference. So this current is flowing through the external resistance as well as the internal resistance. So it will produce a potential difference here as well as here. Okay, so the potential difference produced at the external resistance is I multiplied by capital R. At the internal resistance, it is I multiplied by small r. The same current is flowing through both the resistors, external as well as internal. Same current is flowing. So it produces I capital R at the external resistor and I small r at the internal resistor. The total that gives the total EMF of the cell. So this IR is termed as V potential difference and this I small r as it is. So V potential difference can be taken as equals E minus IR. From this equation, we can take V equals E minus IR. Yes, see this? Getting in the chat. Okay, so you can put any of your doubts in the chat box. I'm not getting any chat. I think JNV Kadapa, is it okay for you? JNV Kadapa. How long was it? Yeah. Right. Okay, fine. We'll proceed. If at all any doubt or you're not following the lesson, please post a message in the chat box. I think it is clear. Okay, now? I'm not getting any feedback. Okay, clear. Somebody posted clear. I think Chamraj Nagar. Yeah. Okay, Pratyusha. Okay, JNV Kadapa, clear. Okay. So I'm proceeding. Okay, fine. If at all anything is there, you can just post a message in the chat box. Don't be a passive listener. All right. So I think this is clear. We can proceed. So internal resistance of a cell in terms of E, V, and capital R. So V equals E minus IR. This you have to remember as a concrete idea. V equals E minus IR. So IR will be equal to E minus V. Okay, E minus V. So dividing all these things with IR, we get, see, dividing this with IR and the E minus V with IR is equal to V. So we can divide it and we get the final equation for the internal resistance as E by V minus 1 multiplied by R. See this, E by V minus 1 multiplied by R. So this is the equation for the internal resistance. Internal resistance. Okay. Now the another most important one, that is Kirchhoff's rules. Kirchhoff's rules. There are two rules. First one is called the junction rule. Second one is called the loop rule. Junction rule is very simple. At any junction in an electric circuit, the sum of currents entering the junction will be equal to the sum of currents leaving the junction. Okay. For the algebraic sum of all the currents at a junction will reduce to 0. The total sum of currents entering the junction will be equal to the total sum of currents leaving the junction. See this one, this is a junction. This one is a junction. So one current is entering the junction, which is I1. Another current is entering the junction, which is I3. Another current is entering the junction, it is I5. And this current is leaving the junction, it is I2. So I1, I3, and I5 are entering the junction, and I2 is leaving the junction. Okay. I4 is again leaving the junction. Now we can write the currents which are entering the junction, it is I1, I3, and I5. So we can write I1 plus I3 plus I5 equals I2 plus I4. I2 and I4 are leaving the junction. It's a very simple rule. The sum of currents entering into the junction will be equal to the sum of currents leaving the junction. So when we make it as an equation, we get I1 minus I2. When this I2 comes to the left side, it is minus, then I4 minus I3 plus I5 plus. It is made into an equation. Now, commonly we take the currents entering the junction or currents reaching the junction is taken as positive, and currents leaving the junction is taken as negative. So it is a common nomenclature. Now, the second one is loop rule. Now, I think this is clear. I think this is clear. The currents reaching the junction is positive and currents leaving the junction is negative. I think this is clear. So the junction rule states that at any junction, the algebraic sum of all the currents at a junction reduces to 0. Now the loop rule. So this is the most complicated rule in these Kirchhoff's laws. Loop rule, the algebraic sum of changes in potential. Changes in potential means V or delta V. Delta V is equal to I multiplied by R. So algebraic sum of all these IRs around any closed loop involving resistors and cells. And of course, the cells also will be there. The resistors will be there. Here we have to put it as IR. And in the cells, we have to put it as EMF. Okay. So the sum of all these things reduces to 0. Okay. Or we can write algebraic sum of all the potential drops and EMFs. It's the same thing. Here, this is the potential drop and this is the EMF. Here again, potential drop and EMF along any closed path. This you should remember, any closed path, along any closed path in an electrical network is always 0. Now we have to follow certain sign conventions for understanding this. Okay, the EMF is taken negative when we traverse from positive to negative terminal of the cell through the electrolyte. That means you have to clearly understand this. This is a cell. Okay, so we are moving from this area to this area. We take the network like this from this area to this area. That means we are traversing through the electrolyte. This is the electrolyte. We are traversing through the electrolyte. So when we traverse from positive to negative, from positive to negative through the electrolyte, from positive to negative through the electrolyte, then the EMF will be taken negative. Clear? And the second one, the EMF is taken positive when we traverse from negative to positive. That is negative to positive. That is, we are moving like this. This is the electrolyte through the electrolyte. So negative to positive. If the current is like this, we take it as positive. And if the current is like that, from positive negative through the electrolyte, from positive to negative through the electrolyte, then it is taken as negative. And from positive to negative, sorry, from negative to positive through the electrolyte, then we take it as positive. This you should understand. Okay. Now, a typical network is given. Let's see in that network. Using Kirchhoff's loop rule, how can we solve the network? Let us consider the loop AFCBA. AFCBA. A is here. F is here. Then C, B, and A. So this network we are considering. When we consider that network, let us see. First one, I1 plus I2. I1 plus I2, whether we take it as negative or positive, multiplied by R1. So forget about these arrows and all. So I1 plus I2, we take it as negative, minus I1 plus I2 into R2. So this is, if this is negative, this also will be negative, R1 and R2. Then, of course, it is coming into this. So it is I1 R5, then E1, whether we take it as positive or negative. Here, it is coming from negative to positive, from negative to positive through the electrolyte, from negative to positive through the electrolyte. So the cell should be taken as positive. So plus E1 equals 0. Then EDCFE, EDCFE. That's E, D, C, F, E. So this one. Here it is from positive to negative through the electrolyte, from positive of the cell to the negative of the cell, positive of the cell to the negative of the cell through electrolyte. So cell should be taken as negative. So that's why minus E2. Then plus I2R3 plus I2R4 plus I1 plus I2 into R2. Then R1 is also there, na? R2, two resistors are there, R2 is there, R1 is there. So in both the resistors, the current is I1 plus I2. I1 plus I2 is flowing through R1 as well as R2. So that is clear. Okay, you can proceed. Then now let us solve some questions from this one. Two cells having EMF of 10 volt and 8 volt. Two cells, one is having EMF 10 volt and second one is having EMF 8 volt. And internal resistance 1 ohm are connected as shown in external resistance 8 ohm. Okay, find the current flowing through the circuit. Read the question carefully. Two cells having EMF of 10 volt and 8 volt, internal resistance 1 ohm each are connected as shown in the. Okay, so this is the diagram. Find the current flowing through the circuit. Here, this cell is having an EMF of 10 volt and the internal resistance of 1 ohm. This is 8 volt and 1 ohm. And we have to find the current flowing through the circuit. Let's see. See here, there is at the junction B, the current which is coming here is getting divided into two. One is flowing through this one, that is I1, and the second is flowing through this one, that is I2. Okay, I1 and I2 divided into two branches at the junction as I1 and I2. Okay, just see this. So using Kirchhoff's rules, we can write I, the total current equals I1 plus I2. Total current is divided into two, I1 plus I2. Then second rule we can apply to the closed path ABYXA. ABYXA. It's ABYXA. This loop we can apply. Okay, so by applying the loop, let's see. So one voltage there is 10 volt and the other voltage there is 8 volt. So 10, we take it like this, ABYXA. So it is from positive to negative through the electrolyte, from positive to negative through the electrolyte. So it is minus. Then here the cell is negative to positive. ABYXA, so negative to positive through the electrolyte. So it is taken plus. Then the first current is I1, second current is I2. I1 is taken negative and I2 is taken positive. Then from this one we get I1 minus I2 equals 2. Then the other loop we consider, that is ABQPA, 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 but the bigger loop. So when we consider that loop, we get similarly that 10 volt it is negative, I1 is positive. Then that 8 ohm, the potential difference developed there is positive. So 8I, so we get an equation 10 plus I1 plus 8I equals 0. Then we substitute a value of this one, that is I1 plus I2 equals I. This one, I1 plus I2 equals I. This we substitute in this equation, equation 3. When we substitute this value in equation 3, what we get? We get here, instead of I, we put I1 plus I2. I equals I1 plus I2 we know, so we put that. So we get 9I1 plus 8I2 equals 10. Then 4 and 2, we can solve it and we can calculate the value of I1 and I2. So I1 is 1.53, I2 is 0.47 and I is 1.06 ampere. Remember the different steps. If you follow certain rules in solving the Kirchhoff's rule problem, Kirchhoff's law problem, it will be very easy. It will be interesting also. Okay. Okay, we move on to the next one. Another problem is given there. This one. This network is given there. So this is a junction. F is a junction. So one current is coming into the junction and two currents are I1 and I2 are going away from the junction. I3 is coming into the junction. So I3 is equal to I1 plus I2. We can write. Then ABCFA. ABCFA. This loop. We consider this loop. And we consider that loop. Let's see what we can write. Plus 1 is 30 ampere. So minus 30 I1. Then from negative terminal to positive terminal through electrolyte. So it becomes positive. So 20 volt plus. Then minus 20 I3. I3 is the current there. 20 ohm is the resistance. So minus I3 into 20 equals 0. Clear? Now 2I3 plus this can be reduced. This equation can be reduced. That is 2I3 plus 3I1 equals 2. Then we can apply the second law to the loop ABDEA. ABDEA with the outer loop. Then we get the same 30I1 plus 20I2. The 20I2 is here. This one. So current is towards this and we take like this. So it is 20I2 plus. So 20I2, then 80 volt. Here again 80 volt. 80 volt is from positive to negative of the cell through the electrolyte. So it is negative 80. It is equal to 0. This can be reduced to 3I1 plus 2I2 equals 8. Then we can substitute the value of 1 in 2. Substituting the value of 1 in 2, we get 5I1 plus 2I2 equals 2. Okay. Then these equations can be used. We can find the values of currents. We get the current as I1 is minus 3 by 4. I2 is 23 by 8. And I2 is 17 by 8. Okay, clear? Now, combination of cells. Cells can be combined in two ways. One is in series way and the second one is parallel way. So each cell is associated with an internal resistance. Cell with an internal resistance. Also, always there will be an internal resistance for a cell, and internal resistance is represented by small r. The EMF of the cell is represented by capital E. Okay, so there are two cells E1 and E2, internal resistance R1 and R2 respectively. They are joined in series. Let's see what happens. Two cells are there, E1, E2, with internal resistance R1 and R2. They are joined in series. Okay. Then V1 as we have learned earlier, V1 will be equal to E1 minus IR1. E1 is the EM of the first cell, and V1 is the potential difference developed across the first cell. Then V2 will be similarly E2 minus IR2. Then V equivalent, the total voltage of the two cells, it will be equal to V1 plus V2, sum of the individual potential differences, V1 plus V2. So V equivalent will be equal to V1 plus V2. Then V1 is E1 minus IR1 plus E2 minus IR2. Then V equivalent, then we can combine these two things, E1 and E2 we can combine, and we can write it as E1 plus E2, and IR1 and IR2 can be combined, and we can write it as I into R1 plus R2. So V equivalent equals E equivalent minus I into R equivalent. So E equivalent is sum of individual EMFs, R equivalent is sum of individual internal resistances. So if many cells are connected in series, E equivalent EMF will be the sum of individual EMFs, and equivalent internal resistance will be the sum of individual internal resistances. Okay, so it is the sum of individual. So it is just like this. Like this, cells are there. This is E1, R1, E2, R2, E3, R3, like that. So many cells are connected in series. Their equivalent EMF is E1 plus E2 plus etc. up to En, and internal resistance will be equal to R1 plus R2 etc. up to Rn. Now, connection of a combination of cells in parallel. What happens when we connect cells in parallel? See, two cells are connected in parallel. Okay, the current from the first cell is I1 and the current from the second cell is I2. Both the currents are meeting at the junction B1, and here the total current is I. So the total current I will be equal to sum of I1 plus I2. Sum of I1 and I2. We have learned that V, potential difference of a first cell, that is E1 minus I1 R1. So I1 can be written as E1 minus V divided by R1. E1 minus V divided by R1. Similarly, I2 can be written as E2 minus V divided by R2. So the total current which is meeting here, so I1, there is an equation, I2, there is an equation. So the total current will be equal to I1 plus I2. Total current I1 plus I2. So I1 is E1 minus V by R1, E2 minus V by R2, like that it comes. Okay, the total current will be like this, E1 by R1 plus E2 by R2, rearranging the terms. Okay, so why we rearrange the terms? Because all the internal resistance are combined together here. Okay, so we get the final equation as V equals E1 by R1 plus E2 by R2, like this we get. Finally, we get an equation V equivalent equals, remember this one, V equivalent equals E equivalent minus I into R equivalent. V equivalent equals E equivalent minus I into R equivalent. And that E equivalent, so there is a shortcut to remember this equation. E equivalent EMF of cells when the cells are connected in parallel. So there is E1 R2 plus E2 R1 divided by R1 plus R2. It's very easy to remember. E1 R2 plus E2 R1 by R1 plus R2 minus I multiplied by, of course, when two resistors are connected in parallel, the parallel combination will be R1 R2 by R1 plus R2. Remember, two cells are connected in parallel, so their internal resistance also will be in parallel. So parallel internal resistance reduces to R1 R2 by R1 plus R2. Then parallel cells the EMF will be reducing to E1 R2 plus E2 R1 divided by R1 plus R2. I think it is very easy to remember. General equation we have for V equivalent equals E equivalent minus I into R equivalent. See, we have seen no, V equals E minus IR. Okay, so when cells are connected, then it will be V equivalent. It will be equal to E equivalent minus I multiplied by R equivalent. So this E equivalent as well as R equivalent you have to remember. It is easy to remember. It's not a tough one. Okay. So the E equivalent equals E1 R2 plus E2 R1 by R1 plus R2. R equivalent is R1 R2 by R1 plus R2. And if n number of cells are connected in parallel, n may be a number that is 8, 10 or 15 cells are connected in parallel, then the R equivalent, 1 by R equivalent will be equal to like this. It goes up to 1 by Rn. And E equivalent by R equivalent. See, the general equation for E equivalent by R equivalent is E1 by R1 plus E2 by R2, like that it goes. And if there are n cells, there will be n terms. 2 cells are there, 2 terms are there. So if there are n number of cells, there will be n terms like this, E1 by R1 plus E2 by R2, like that, En divided by Rn. Okay. All right. Now the Wheatstone's bridge. See, it's a particular arrangement of 4 resistors. Remember one thing I missed. See, there are 2 cells like this. If 2 cells are connected like this, this is E1 and this is E2. What is the equivalent EMF? Equivalent EMF will be equal to E1 plus E2. And if the 2 cells are connected like this, remember, this is E1, this is E2. Here the equivalent EMF will be equal, whichever is greater. Here this is E1 is greater than E2. Okay, so this one will be equal to E1 minus E2. So while solving problems, you have to remember this. If 2 cells are connected in this manner, in a series manner, the EMF, effective EMF will be the sum of individual EMFs. And if 2 cells are connected like this, okay, so that will be the difference in the EMFs. This also you have to remember for the exams. All right. Now let's move on to Wheatstone's bridge. Okay, so it's an arrangement of 4 resistors. 4 resistors are arranged at the 4 arms of a network. So that is called a Wheatstone's bridge. 4 resistors are there, P, Q, R, and S. P, Q, R, and S. Currents are also there, I1, I2, I3, and I4. So the total current comes here. So generally the current means a flow of electrons. Electrons are flowing from negative of the cell towards the positive of the cell. Since electrons are having negative charge, we take the direction of current as opposite to the direction of flow of electrons. Remember, electrons are flowing from negative of the cell to the positive of the cell. Since electrons are having negative charge, we take the conventional direction of current opposite to the flow of electrons, that is from positive to negative. So the current reaches here. It is divided into I1 and I2. I1 reaches here, I2 reaches here. And if there is a potential difference between B and D, so it will flow through this one. Otherwise, it will not flow. And current here is I3 and the current here is I4. Okay, let us see. four resistors P, Q, R, and S. Four resistors kept there, and in the middle point between B and D, there is a galvanometer connected. All of us know that galvanometer is a device which is used to detect feeble values of current. So for measuring strong values of current, we have ammeter as well as milliammeter and all these things. Feeble values of current, for detecting whether the current is present or not, for that only we use galvanometer. Okay, so the arm AC is, there are two arms, one is AC and the second one is BD. Arm AC is called the battery arm, and the second one BD, the arm BD is called the galvanometer arm. Okay, so when we can say the bridge is balanced, when the current through the galvanometer reduces to 0. That is, there is no current through the galvanometer. Ig reduces to 0. Then we can say that the bridge is balanced. So that's why I told that the galvanometer is kept there to detect, to identify whether there is any feeble, any minute, any small values of current flowing between B and D. Okay. So the total current which is coming here is I. The current which is going through the P, it is I1. It is going through the R, it is I minus I1. So the total current is I1 is going. So remaining current I minus I1 will be coming through the resistor R. Okay. At the junction, it is divided into I1 and I minus I1. And at the junction B, the current is again divided into Ig and I1 minus Ig. The current reaching here is I1. This is I1. And if there is a current flowing through this one, it is Ig. The remaining current will flow through this one. That is I1 minus Ig. This Ig will come here. This I minus I1 and this Ig will meet, and that becomes I minus I1 plus Ig. I minus I1 plus Ig. Okay. So the current entering the junction is I. The current leaving the junction C. Current entering the junction A is I, and current leaving the junction C is again I. So it is a loop. Okay. So now let us try ABDA. ABDA. That loop we can take. Then first one is I1P. So the current is going up. The current is going up. So it is minus I1 multiplied by P. Then the current direction is like this. So minus Ig multiplied by G. Remember, minus I1 multiplied by P minus Ig multiplied by G. So it is going opposite to the direction of current. So it becomes plus I minus I1 into R. Okay. So this loop we are considering. First one is I1 and P. It is in the same direction of current. So we take negative. So minus I1 into P. Then this one, Ig and G, it is in the same direction of current. So we take negative, minus Ig into G. Now this is opposite to the direction of current. So we take positive. So I minus I1 into R equals 0 as per the Kirchhoff's second rule. Okay, see the next one. BCDB. See the loop BCDB. BCDB. The loop, the side BC, current is in the same direction. So minus of I1 minus Ig multiplied by Q. Again, opposite to the direction of current. So it will be plus I minus I1 plus Ig. I minus I1 plus Ig multiplied by S. Then again, opposite to the direction of current. So it will be plus Ig multiplied by capital G equals 0. Clear? ABDA and BCDB. All right. Now, if the current in the galvanometer is 0, that is Ig is 0, there is no current through the galvanometer. Current through the galvanometer reduces to 0. Ig reduces to 0. What happens? The first equation, I1P minus I1P plus I minus I1 into R equals 0, as it is no change. But the second, so the first equation can be written as I1P equals I minus I1 into R. The second equation is minus I1. So this reduces to 0. So minus I1 into Q plus I minus I1. This reduces to 0. I minus I1 multiplied by S. Then this reduces to 0. Okay, so that the second equation comes to I1Q equals I minus I1 multiplied by S. So we have equations 3 and 4, most simple equations. We have I1P as well as I1Q, and dividing equations 3 by equation 4. Equation 3 divided by equation 4. So we get I1P. So this is I1P divided by I1Q. It will be equal to I minus I1R divided by I minus I1 in S. So this getting cancelled, I1 and I1 get cancelled. So this one get cancelled. So we get the final equation as P by Q equals R by S. See this one, the complete idea about the Wheatstone's bridge. The condition here, condition what we applied here is there is no current through the galvanometer. So there is a question arises. Then if we calculate the conditions when no current is flowing through the galvanometer, then what is the use of galvanometer there? So obviously this question arises. The use of galvanometer there is to adjust the values of P, Q, R, S and all these things to make the reading in galvanometer 0. Initially, the galvanometer reading may not be 0. We will adjust the value of any one of these one. So generally we adjust the value of S. Adjust the value of S so that the deflection in the galvanometer reduces to 0. So when the deflection in the galvanometer reduces to 0, then we can say that this bridge is balanced and there is a perfect ratio of resistors. And this Wheatstone's bridge is supposed to be a more accurate device than other devices for measuring resistance. So we are comparing, or we are measuring resistance only ultimately. So this is a more accurate device. The reason there is, in all other devices, just like Ohm's law and all these things, whenever we measure voltage and current, so there is a current flowing through the device. And here in this device, we arrive at a null deflection condition. That means no current is drawn from the cell. Null deflection condition. Bridge is balanced. Galvanometer shows null deflection. So there is no current through the galvanometer. No current is drawn from the cell, like that. So this situation, if there is no current, then the readings will be more accurate, because we know when current is flowing through a resistor, little bit of heat will be developed. And again, we know little bit of heat is developed means its resistance will be varied. So in the other measuring techniques, we may not be getting an accurate reading of resistance. Here we are getting a more accurate reading because the current through the galvanometer is 0. See this one, see. Okay. So this idea can be used in the devices like meter bridge. Of course, this meter bridge and all, it is removed from the syllabus this year. Anyway, this is the application of this Wheatstone's principle. Now, electrical energy, that is also included this time, electrical energy. It is, we know energy is a work done. It is a capacity to do work. Energy is a capacity to do work. So here the work is done to maintain the flow of current in a conductor. So current is required, and for making that current possible, to maintain a current in a conductor, how much work we have to do, that is called the electrical energy. Okay, so if Q is moved through a potential difference of V in time t, then the work done is Q multiplied by V. Then V, the Q can be taken as I multiplied by T, then the work done will be equal to V multiplied by I multiplied by T. So that is V can be taken as I R as per Ohm's law. So work done equals I square RT. I square RT. Work done equals I square RT. R is a resistor, I is a current, T is the time. So this work is the electrical energy. Okay, so electrical energy equals I square RT. So this can also be written as I is equal to V by R. So this can be written as I equals V by R. So when we substitute this value, E equals I square RT. So V by R whole square RT. V square by R square into R multiplied by T. That reduces to V square by RT. V square by R multiplied by T. The unit of electrical energy is joule. Then electric power. Electric power is the rate at which work is done. So here the electric power means the rate at which electrical energy is used or work is done. Then electrical energy divided by time. Then electrical energy, we have developed an equation. It is I square RT divided by T. So it is I square T. So I into R, here again I square T, P equals I into R multiplied by I. So I into R is V into I. So we can write it as power equals voltage multiplied by current. Or we can write it as V square by R. Instead, we can write I equals V by R. So power equals V into V by R. It is V square by R. You can write that also V square by R. The SI unit of power is watt, and it is represented by capital W. Remember, always you have to write the power of electrical, the unit of power as watt. Watt means capital W. Okay. Of course, we have bigger units. Kilowatt and megawatt are the bigger units of power. Then the Joule's law of heating. Okay, this you know, you have learned it in class 10. Okay, so the heat developed is directly proportional to the square of current, resistance, and time. Okay, so that is the Joule's law of heating. H is proportional to I square, square of current. H is proportional to R, resistance, and H is proportional to T. So altogether, it is proportional to I square RT. Okay, so it is I square RT. Now let's see some numericals. The first one, the number density of conduction electrons. Number density of conduction electrons in a copper conductor estimated is 8.5 into 10 power 28 per meter cube. Okay, how long does an electron take to drift from one end of a wire 3 meter long to its other end? Area of cross section is given as 2 into 10 power minus 6 meter square, and it is carrying a current of 3 ampere. So the given quantities here are n, number density, length is given there, area is given there, current is given there. So which equation we have to use? We have to calculate how long, that is the time we have to calculate. So we have to use this equation, I equals NA VD multiplied by E. N is given there, A is given there, VD is not there. Okay, so VD we have to calculate. So I equals NAE, then time is, as I told earlier, VD means it is velocity. So it is L by T, we can write distance by time. So that the same concept we can apply here also. Time is equal to L by VD. Okay, just try. Right, when we try it, we can just substitution only. Substituting the values. All other parameters are given there. Okay, we get the value as 2.72 into 10 power 4 seconds. All right. Okay, move on to the next one. A wire of length 3 meter and area of cross section 1.7 into 10 power minus 6 meter square has a resistance of 3 into 10 power minus 2 ohms. Calculate the resistivity of the wire. Resistivity of the wire. So L is given there 3 meter, area is given there this much, resistance is given there. It's a very simple one. Rho L by A, rho L by A, direct question. Rho equals RA by L. Direct question it is. When we substitute, we get a value of 1.7 into 10 power minus 8 ohm meter. Value of unit of resistivity is ohm meter. Remember, if you do not write the unit at the time of examination, board examination, they will reduce half mark. Okay, very simple one. Then another one, another simple one. Length L, area of cross section A, and resistance of 20 ohm. What will be the new resistance and the resistivity of the wire if it is stretched to double its original length? This kind of this is a very simple one. Okay, so it is stretched to double its original length. So I1, A1, R1 are the initial length area of cross section resistance. R1 equals 20. It is stretched to double the length. Area of cross section becomes half. Remember, when an element of length L is stretched to double its original length, its length becomes 2 times, and at the same time, its area of cross section becomes half, because material is not newly added. The same material is being stretched to double its original length. So its length doubles and area of cross section becomes half. Okay, so I2, A2 and R2. So this R2 becomes 80 ohms. Okay. Next one, electric toaster uses nichrome for its heating element. negligibly small current passes through it. Its resistance at room temperature is found to be 73.3 ohms. When the toaster is connected to 230-volt supply, the current settles after a few seconds to a steady value of 2.68 amps. What is the steady temperature of the nichrome element? The temperature coefficient of resistance, nichrome average over the temperature range involved is 1.7 into 10 power minus 4 per coulomb. Now R1 is given, T1 is given, V is given, I is given, alpha temperature coefficient is also given. R2 we can calculate. So this is the core equation. This you have to remember. R1 into 1 plus alpha, T2 minus T1. This time we are expecting a question from this area. And when we calculate, we get the final answer as 847 degrees Celsius. 847 degrees Celsius. Only this equation is crucial. If you get this equation, all other things are very easy to solve. Okay. Temperature coefficient of resistivity of silver. Again, same thing. RT, the same equation. RT equals R0 into 1 plus alpha T. R0 is given. Alpha you have to find out. You'll get the value of alpha. Sorry. You can find the value of alpha by solving the above equation. Now this time, you take this question and post the answer. Okay. The storage battery of a car has an EMF of 12 volt. Internal resistance of battery is 0.4 ohm. What is the maximum current that can be drawn from the battery? You have to solve this question and post your answer in the chat box. Come on, quick. Solve this question and post the answer in the chat box. Or you can even open the mic and tell me the answer. Just to switch on the mic and tell me the answer. Come on. It's very simple. Nobody's there. So this E equals I into R. Maximum current I equals E by R. E is 12 volt and R is 0.4. So that is the answer. So it comes to how much it will be? 30 ampere. Anybody got it? Let me check. Yeah. Yeah, Chamranagar, they got the answer. Very good, very good, very good, very good. Now the next one, be ready for the next one. So this is the next problem. Be ready. A storage battery of EMF 8 volt and internal resistance 0.5 ohm is being charged by a 120 volt DC supply using a series resistor of 15.5 ohms. What is the terminal voltage of the battery during charging? What is the purpose of having a series resistor in the charging circuit? Come on, come on, come on, do it. Either you open or switch on the mic and tell the answer, or drop it in the chat box. Okay, come on, come on. Yeah, Bidar is coming with the correct answer. Bidar, 11.5 volt. Excellent. Bidar, JNV Bidar. Very good, very good, very good. Okay, let's see how we can solve it. So V dash will be equal to V minus E. So that is 120 minus 8. It is 112 volt. 112 volt. Then current I will be equal to V by plus R. That is 112 divided by R is 15.5 plus 0.5. That is 112 divided by 16. So finally the current reduces to 112 by 16. So it comes to around 7 ampere. So around 7 ampere. The question is, what is the terminal voltage of the battery during charging? What is the purpose of having a series resistor? Terminal voltage of the battery during charging that we need. Okay. So voltage across R1 we need. So voltage across R1. Voltage across R1. It will be I into R1. Is 7 into 0.5. That is equal to 3.5 volt. Okay. So now we need the terminal voltage. What will be the terminal voltage? Terminal voltage will be 8 plus 3.5. 11.5 volt. Okay. So the use of a series resistor here is to limit the current. So during charging, the current should not exceed a particular value. So for limiting that current, we need a series resistor. That is the purpose of having a series resistor in the circuit. Okay. So one more question I have. You take this question and just send the messages. Okay. So the question is like this. So this one, take this question. We are running short of time. Take this question and do it and post the messages to my WhatsApp or in the chat box. Okay. Thank you for being with me. We'll meet again in the afternoon at 2:30 p.m. Okay. Thank you.